In this video, we're going to talk about the preparation and reactions of carboxylic acids. Now, most of these reactions we've already seen before, and so they're probably already in your reaction journal, but what I might recommend is putting them in your journal again so you've kind of got all these related reactions together. We've already encountered a number of different ways of preparing carboxylic acids. Last semester, when we learned the reactions of alkynes, we learned that oxidative cleavage of an alkyne would cut the triple bond here, and then each R group, where it had been a triple bond, would be replaced by the carboxylic acid. Then at the beginning of this semester, when we learned about reactions of alcohols, we learned that oxidation of primary alcohols would produce a carboxylic acid. And then when we learned about reactions at the benzylic carbon, when we had benzene rings, oxidation, again with sodium dichromate, would chop off whatever was at this benzylic carbon and replace it with a carboxylic acid. This is another reaction that we've seen before. We can convert a nitrile into a carboxylic acid by heating it under acidic conditions. And as we talked about last chapter, this allows for a two-step synthesis of a carboxylic acid from an alkyl halide. So if I start with an alkyl halide, I can then react it with cyanide ion, and so our reagent would probably be something like NaCN, where the sodium just acts as a counter ion, and this is an SN2 reaction where the cyanide ion replaces the halogen, and then I can do the hydrolysis of the nitrile to convert it into the carboxylic acid. Now, if you'll notice, in this synthesis, we're adding an additional carbon atom to the original compound. Right? This compound had one carbon atom coming off the benzene ring. Our final product has two carbon atoms. So we're not just converting the alkyl group into a carboxylic acid, we're also adding a carbon in the process. All right, this is a new reaction for preparation of carboxylic acids. And in this case, it's carboxylation of a Grignard reagent. So this is where we have something like RMgX, where our active ingredient, if you will, is the alkyl group with a negative charge here. If we react that with carbon dioxide, it'll produce a carboxylic acid. Now, we have to do it in two steps because the result of the reaction of the Grignard reagent with carbon dioxide is to first produce the carboxylate ion, and then in a separate step, because as we've learned, acids don't play well with Grignard reagents, so in a separate step, if we add a proton source to convert the carboxylate ion into the carboxylic acid. And so, in addition to the last slide, this gives us a second method to convert an alkyl halide into a carboxylic acid. And again, we're adding an additional carbon. In this case, if we start with the alkyl halide, we can convert that into a Grignard reagent by reacting that with magnesium. The diethyl ether serves as a solvent in this case. That gives us the Grignard reagent. We then react that with carbon dioxide in the first step, do an acid workup in the second step to give us the carboxylic acid with an additional carbon. Right, because here we have no carbons coming off the benzene ring. Now we have one carbon coming off the benzene ring. All right, the main reaction of carboxylic acids that we're going to look at is the reduction of carboxylic acids. And we've already started to research this topic back in the chapter on alcohols. And we learned that we could produce alcohols from the reduction of a carboxylic acid with lithium aluminum hydride. And so, now we're considering it from the carboxylic acid side, right? We can react a carboxylic acid with lithium aluminum hydride to produce the primary alcohol. And if we look at the mechanism, the first thing that happens is the fact that lithium aluminum hydride is a strong base. The first thing it's going to do is it's going to deprotonate our carboxylic acid to give us a carboxylate ion. In the second step of the mechanism, the carboxylate group is converted into an aldehyde. Now, I'm not going to ask you to know this whole mechanism, in particular because this second step is somewhat speculative. But what we think happens is the hydrogen is attached to the carbon here, then the pi bond becomes a new bond with the aluminum, and then in the final step to produce the aldehyde, the oxygen in the aluminum takes off as a leaving group, and one of the lone pairs comes down to form the double bond and make the aldehyde. Now, the final step to convert the aldehyde into a primary alcohol should be familiar because this is a nucleophilic addition reaction that we studied last chapter. In this case, the nucleophile is a hydride ion, and so the hydride ion attacks the alpha carbon, which and then the pi bond becomes a lone pair on the oxygen, and then we have a acid group serving as a proton source to give us the primary alcohol. Now, what I do want you to know about the reduction of carboxylic acids with lithium aluminum hydride, while I'm not going to ask you to know the mechanism, what is important to know is that we can't stop at the aldehyde. When we use lithium aluminum hydride, we will go all the way from the carboxylic acid to the primary alcohol. Now, there is an alternate reagent that can be used to reduce carboxylic acids to primary alcohols, and that is borane. So if we use BH3 and THF, similar to the reagents that we used in the hydroboration oxidation when we studied reactions of alkenes, that will convert our carboxylic acid into a primary alcohol. The reason we talk about borane in addition to lithium aluminum hydride is that borane is chemoselective. It will react with carboxylic groups and not react with other carbonyl groups. So for example, if we treat this compound with lithium aluminum hydride, it's going to convert both the carboxylic acid and the ketone into alcohols. But if we treat it with borane, because borane is chemoselective for the carboxylic acid, it's going to leave the ketone alone, and it's only going to convert the carboxylic acid into the alcohol. It's going to leave the ketone alone. All right, I want to finish off this video with a couple synthesis examples from reactions that we've learned in this video. So I want to convert this compound into this one. And one thing I notice is that the carbon skeleton has changed. I've added an additional carbon atom to my starting alkyl halide. And I know in two of the reactions that we've learned, we can convert a alkyl halide into a carboxylic acid and add an additional carbon through hydrolysis of a nitrile or through reacting a Grignard reagent with carbon dioxide. And so I'm going to go with the first one, the hydrolysis of a nitrile. So I can convert this into a nitrile by first doing an SN2 reaction. And so that cyanide is going to replace the bromine, which is going to be a leaving group. Then I can heat that under acidic conditions. And that will convert my nitrile into a carboxylic acid. And then I know I can go from a carboxylic acid to a primary alcohol through reduction. And so I can use either borane or lithium aluminum hydride. And so I'm going to go the borane route to convert my carboxylic acid into the primary alcohol. Okay, in this case, I have the same starting material, but I want to end up with a carboxylic acid. Now, I can't use the method to convert a alkyl halide into a carboxylic acid that I used last time because the method I used added an additional carbon atom. And in this case, we didn't do that. And so I need to think about other ways that I can make carboxylic acids. So I can do it with oxidative cleavage. If I could put a triple bond on here. But I could also make carboxylic acid from a benzene ring that has a benzylic carbon. I don't have a benzene ring, so that's out. So the other way I know to make carboxylic acids is through oxidation of primary alcohols. And so what I want to do is convert this into an alcohol. Then I can oxidize it to get the carboxylic acid. So to convert that into an alcohol, because I have a primary alkyl halide, if I react that with something like NaOH, which is a strong base and a strong nucleophile, because I have a primary alkyl halide, the SN2 reaction will dominate over E2. So that will give me the primary alcohol that I want. And then we can use sodium dichromate to convert our primary alcohol into the carboxylic acid.